Hi guys. In the last video, the topic was multiple translation units, and you will see the upcoming topic in this video, storage classes external and static, will be related to that. In the demo, I will show you an example with two translation units. One of them is this foobar.c, and it contains a function bar and the global variable foo. And for some reason, it's very important that other translation units have access to this global variable and to this function. So what we do is we write a header file with the declaration of this function bar and the declaration for this global variable foo. And of course, we also include this header file. And that's it for this translation unit. Then the other translation unit will include this header file, and it will access both the global variable and this function bar. So that's already it. And what possibly could go wrong here? You see, everything is already prepared, and I also have this make file from the last session, so I just have to use make to generate an executable, and nothing went wrong. But recall that on my computer, Clang is the default compiler, and I also want to test this with GCC. So I will just use make together with cc equals gcc-11. That's my GNU compiler. And then I do get an error. Actually not from the compiler, but from the linker. Now this is kind of the worst, that you sometimes have a problem on some platforms and on other platforms not. It means that our code is not portable. So what went wrong, or what can go wrong in general? Well, if we look at what the compiler gets from the preprocessor, then of course it gets the complete header file from the standard IO header and this declaration of function bar, but it also gets this line for the declaration of variable I. But actually this is not only just a declaration, it's a definition of an uninitialized variable. And that means some data gets generated from it. And in this case on a BSS segment. And that means after the assembler generated this object file contains a simple foo. Now, when we look at the other translation unit, then of course here we also have a definition of this variable. And that means also some data gets generated in the object file, in this case in the data segment. But that means if the linker looks at both object files, both contain a symbol with the same name, and here we have this name conflict. So this is what went wrong, at least in the second case. Why it not always goes wrong is about certain features that can be used by the compiler and by the linker. Details about that I can provide on the website. The important thing is that it could go wrong, and we have to write portable code. So because header files are included, we have to make sure that they do not contain definitions, just declarations. And I call this pure declarations. And here I already fixed that with this keyword extern, which is meaning exactly that here we have a pure declaration. Function declarations are by itself already pure declarations, so here you actually do not have to use this extern keyword. But I'm currently thinking about changing my coding style, so far I'm not using it, to also use the extern keyword in header files to make it more consistent. Now I will show you that this actually solves the problem, at least for GCC. I mean, it's not a proof that it solves the problem in general, but it will actually solve the problem if all the tools behave correctly, standard conform. So it's still working with Clang. And now it's also working with GCC. In the second example, I also will show you two translation units. The test program will call a function bar, which will be defined in the other translation unit. And let's say for debugging purposes, we first want to print a message like, now we will call function bar. And internally, inside of this test program, we will outsource this important task to a function. And because foo is such an obvious name for this functionality, we will call it foo. So foo prints, now I will call bar in that meaning. And in this other translation unit, we have this implementation of function bar, and also for debugging purposes, we want to print now function bar is done. And also we outsource this to a function inside of this translation unit, and we will also use the function name foo. Now here you already might guess now what the problem will be. Of course, the linker will see this symbol in the object file for this translation unit of the test program and for this translation unit of bar.c. And I will already show you here, this is kind of a spoiler, how to fix that problem. You have to declare this internal functions as static. So here the example from the slides, and as promised, this gives you a linker error. Now interesting is to use here again this command nm for seeing the names that the linker actually will see. And then you can specify some object file. Those were already generated. And then you see here, these are the symbols in the symbol table. And if you see an uppercase letter, it's seen by the linker. And if it's a lowercase letter, it's invisible to the linker. And you see here the symbols for bar, underscore bar actually, and underscore foo are visible. And also in this test program object file, you also have these symbols. Now, if we change here this declaration of the function to static, and also here to static, and run make again, and again look at the symbols that the linker actually can see, bar.o, and the object file for test program, you now see that this function foo is here listed with a lowercase letter t, and that means the symbol exists in the symbol table, but it's invisible to the linker. And that's actually the solution to the problem. We just declare all the functions that are only used internally inside of a translation unit as static. So another rule of thumb, if you do not implement a function that will be somehow used by others, which is not declared in the header file, it should be always static. Of course, you also can declare global variables as static, then you can use them inside of a translation unit, and you do not run into problems because the linker will not see this symbol, so you do not have this name conflicts if in other translation units the same name is used for a function or for a variable. But the interesting thing here is that you also can declare static variables inside of a function. And then it seems as if you would have a local variable with the special feature that this variable remembers what value it had the last time this function was called. But you will see in the demo that actually these static variables, even if they are declared inside of a function, are always global variables. So this declaration of this variable bar inside of function foo looks like a local variable of function foo. So it seems like this variable will be initialized when you call the function foo the first time. But when we look into the assembly code generated from this translation unit, you will see that it's actually technically just a global variable. And global variables are initialized before the first instruction of the program gets executed. And now before I look into the assembly code, let's first see what this program is doing. So of course it's counting from 1 to 42 and prints out this message. Now in this case, let me also show you that by coincidence, I saw that at least on my platform, I would get the same behavior if I just declare this variable bar as a local variable like that. So it seems as if this would be a bad example because you do not see a special effect if you use this static keyword or not. But this here is obviously kind of luck that we get the same result, and we already know about stack frames, how they work, and that this variable bar each time gets the same location on the stack, so it reuses by coincidence this value. But this would be not portable code if we would, for example, add here another function dummy. Also with a local variable with value 1, 2, 3, and this function gets called once before this for loop. Then you will see counting begins not at 1, at 123. So this is certainly kind of luck what we get. Now change this back to static and initialize it with 1. And then we have portable code. Now let's look into the assembly code. And I will just search for a symbol bar at the beginning of a line followed by a colon. And here it is. And from the assembly programming part, you see this is a global variable. And you also see that the name of this label somehow contains this name of the function. If I would define a variable outside of this function, for example here, then in this case you will not see a second label. Let me show you that. This is also kind of good way to show you that certain optimizations can be done if you have static global variables. So I search again for a label bar. And actually this is the only label bar, or the only label that contains bar in this program. So no second symbol bar was generated. This is because this variable bar is nowhere used. The compiler sees that this bar is different from this, of course, because it's in a different scope, nowhere used, so I generate code for it. Now let's use it, for example, here. And now I have two labels where bar occurs, and this here is this variable bar defined here in the third line with initial value of 32, and this here is variable bar declared or defined inside of function foo. Now let me also show you the difference in the assembly code, whether you use this static keyword or not. Let's remove it here, and then let me also change this here back. So recall before, when I did not use this global variable, no symbol was generated and no data was generated because it was used nowhere. Now it's no longer static, and then you will see the compiler still has to generate code for this global variable bar, because after linking, some other translation unit might require this variable. So the compiler doesn't know whether somewhere else it is needed or not. So now this label is back, and also we see here the value 42. And what is the difference here? The difference is here. This is a directive to the assembler. This global directive basically tells the assembler that this should be an entry in the symbol table that later should be visible to the linker. And you will also see this in the symbol table that we can see from the object file. You see here the label underscore bar has this uppercase D, so it's in the data segment and visible to the linker. This is the symbol generated from this static integer variable bar inside of function foo, and it's invisible to the linker. That's it for this video. On the website you will find more information about this topic, also about certain edge cases that the language specifies. Is it allowed to declare something first external and then a static, or the way around? Why would it make sense at all? What we also should discuss maybe in class is when or whether you should use global variables at all. When should you declare global variables in a header? Why is this often a bad thing, but why is it sometimes needed or could have an advantage? What is the advantage, disadvantage of using static variables inside of a translation unit as a global variable or within a function? Things like that.